Hello everyone, welcome back to BC Calculus. We're in lesson number 31 where we're talking about volume. More specifically, we've been talking about the shell method. In this video, I'm going to do a comparison of the washer-disk method and the shell method. Before we get to our three examples, I just want you guys to see really quickly that this is a nice little visual of showing you guys how the difference between the disk and the shell methods. And I keep saying disk here, but it's the washer-disk method. When we draw our rectangles, remember for our washer-disk method, they're always going to be perpendicular to our axis of rotation. And also, if you guys look at the equations, we're only going to pull out a pi, and we have to find our big R and our little r, which we will do in many examples before. We've already done those. For our shell method, we pull out 2 pi, and then we have to worry about our radius, our height. Our height's always just going to be our differences of our curves, whether it's top, bottom, or right, left, and then our dx or dy, pertaining to which one we're looking at. And again, this one's going to be parallel to our axis of rotation. I'm not sure if I said that or not, so I'm going to say it again. So let's look at these examples. Now, I'm going to tell you guys really quickly that when I do these three examples with you, I'm going to choose the method that's best suited for these particular axis of rotations. So basically, which one would create only one integral. So let's look at the first example. And again, we're just trying to find the integrals. That's going to find the volume of a solid resulting in the region R, which is given to us here, shown below, and we're going to revolve around these four things. So the first one's the x-axis. So if I look at the x-axis, and so I'm revolving around that first, so part A, I can create a rectangle that is perpendicular to my axis. And what's awesome about this, two things, or actually, first, it's flush to the axis, so that's awesome. So that's pretty easy. And the second thing is no matter where I draw my rectangle, no matter where I draw it, my top function is always this curve, and my bottom function is always the x-axis. So I know that I can use the washer-disk method here because, again, it's perpendicular to my axis of rotation. So I'm going to go ahead and use the washer-disk method here. And so I'm going to do volume is equal to, I'm going to go ahead and pull out the pi because washer-disk. We all know that this is going to be 0 to 3 from just our knowledge of the washer-disk method. And then remember that because it's flush to our axis of rotation, we don't have a little r here, we just have a big R. And the big R is going to be the top curve minus the little curve. So our top curve is going to be 3 plus 2x minus x squared. Our bottom curve is going to be minus 0, right? It's going to be 0. So I'm going to leave that alone. And then, actually, I'm going to go ahead and put it here. Why not? And then remember that we have to square it because we're going to create ourselves a circle, right? A circle. So it's going to be pi r squared. And then we're going to go ahead and do our change of x. So that's how we solve that very first problem. Okay, so let's look at part B now. We want to revolve around the y-axis. So we're going to go ahead and revolve around the y-axis. And so we know that this is going to be a shell method problem because if I draw my line perpendicular, and notice that that's the first thing I'm doing, is you want to draw it perpendicular. And if you look at it here, my right curve is going to be this function. My left curve is going to be the y-axis. But if I draw right here, again, perpendicular to my axis, then my right curve and my left curve are actually the same function. So I don't want to use the washer-disk method. And I think that's probably the easiest way to differentiate between whether we use the shell method or use the washer-disk method. So now let's go ahead and draw something that's parallel. So parallel to it. And since our axis now is parallel to our rectangle, then we know we want to use the shell method. The other thing about this is the fact that since, again, what we always remember that this was in terms of x, well, this is also going to be in terms of x because you always decide which axis is this perpendicular to, tells you what we're going to do. So this is going to be a change in x. So we're going to go ahead and pull out a 2 pi, and then we're going to integrate from 0 to 3. Our radius is going to be from the axis of rotation, well, actually from the y-axis, I should say. This actually happens to be the axis of rotation, but it's always from the axis to our rectangle. Remember, the radius is always from our axis to our rectangle. So this is going to be our x. So our radius is going to be x. Our height is going to be top function minus bottom function, just like when we did area. And actually what we did over here as well. No squaring, and then dx. All right, so we have our 2 pi, we have our r, which again is the circumference of our circle, we have our height, and then we have our width of our rectangle. Okay, so let's look at the next one. It says y equals -1. So we're going to go ahead and revolve around y equals -1, which is going to be right here, somewhere y equals -1. So again, we draw our rectangle, and we draw a rectangle, we realize that this is going to be perpendicular to our axis. So again, we're going to use our washer disk method for this one. And so we're going to have our pi, again, 0 to 3, nothing changing with this. And we're going to then realize that we have a big R and a little r because we are not flush, right? Our axis has a little bit of hole here, so this would create ourselves a little disk that looks like this. And so our big R is going to be, as we remember before, it's going to be the curve that's furthest away from the axis of rotation, and it's going to be the curve minus the axis of rotation, because yet again, guys, it's always top minus bottom. So since the shaded region is above the axis of rotation, we're going to do this first. So the big R is going to be 3 plus 2x minus x squared, and then we're going to do minus our axis of rotation, which is negative 1. Negative 1. So our big R is going to be 3 plus 2x minus x squared plus 1. And we have to square it. So that's what big R is. And then little r is going to be this little distance right here. It's going to be the curve that's the closest to our axis of rotation and the difference between that and the axis of rotation. So this is going to be y equals 0. So our little r is going to be top, which is 0, minus a negative 1, which is positive 1. And again, you guys can see that. So it's going to be this minus 1 squared, and then again we have our dx. So big R minus little r gives you our outside part. So there we go with that one. And finally, we're going to do the line x equals 4. So that would be somewhere around here, x equals 4. And just again, we're very good about drawing our rectangle. And notice that for all 4 of these questions, our rectangle always looked like this. So if this was parallel, then we use the shell method. If it was perpendicular, we used our washer disk method. So this is going to be a shell method as well. So we're going to do 2 pi, and then we're going to integrate from 0 to 3, so that doesn't change. Now this one's really good because we're going to use our radius is actually not simply going to be x. So remember, again, the distance between our axis and our rectangle, this is x. And my radius is going to be this, because remember, we're revolving it around this line right here. We're revolving it around this line. So this is going to go around this way. So the radius is going to be this. Now, because, again, it's going to be right minus left, if this whole distance is 4 and this little guy is x, then this is going to be the difference of 4 minus x. So our radius in this particular example is going to be 4 minus x. So we're going to write 4 minus x. And that's, again, I think the easiest way to remember that is that the distance between the axis and your rectangle is either the x or y, based on determining what that is, and then the radius is going to be the difference between the axis of rotation and that value. And then the height is not going to change, right? The height's still going to be what you see right here. It's going to be 3 plus 2x minus x squared, and that's going to be multiplied by delta x. All right, so you guys have seen that one already, and I've decided that based on the time that I have left, I'm going to go ahead and jump down to example number 6 and do this particular problem with you. For this one, it says consider the region, and notice it's just given as our functions, g of y and f of y, and it's asking us to set integrals for the volume of the solid obtained of R given these particular examples. So first thing I want to do about every single one of these problems is that if I were to draw a rectangle that looks like this, great, but then over here it's a little bit of a mess, right? I can't create myself a rectangle because of all the craziness, the jaggedness of this problem. So for every one of these problems, we're going to create our rectangle based on the fact that it's going to look like this. So no matter where I draw my rectangle, this way, in this orientation, this is always the right curve and this is always the left curve. So the bottom line now, if this is probably one of the last times I'm hopefully going to say this, is that since my rectangle is always going to be in this orientation, then if I'm rotating something that's parallel to this direction, to these rectangles, then I'm going to use the shell method. And if it's perpendicular, then I'm going to use the washer disk method. That's probably the easiest way for me to tell you guys that. So there's our little pretty picture that I'm getting ready to erase because I just want to do one rectangle. And let's go ahead and look at the first example. So we're going to rotate around the x-axis. So one more time, I'm going to draw myself a little rectangle. And it's going to be parallel to the x-axis. Therefore, I'm going to use the shell method. I'm going to use the shell method because it's parallel. So I'm going to go ahead and pull out a 2y. And since, again, I'm looking at right minus left, then I know everything's all about y in this particular example. And so remember, when we integrate our bounds, it's going to be top and bottom. So we're going to integrate from c to d. And so our radius is going to be the distance. Well, first of all, what we need to do is figure out that the value from the axis to our rectangle, this is going to be y. This is going to be y. And so our radius actually ends up being y because the axis of rotation that we're looking at is actually our axis. So that's actually pretty awesome. So guys, when you're doing the shell method and you're rotating around the x or y axis, then whatever your radius will always be either the x or y based on the orientation of what your thing is. Always, always, always. If it's a line, then it's going to be something else. And then all we need to do is talk about the height of this thing. Well, the height is going to be the right side curve minus the left side curve. So we're going to get f of y minus g of y. And then the last thing we have to do is just take into account the thickness or the width of our rectangle. And this is going to end up being dy. So that's how you solve that particular problem. Okay, let's look at the y-axis. So now we're going to rotate around the y-axis. Well, in this particular example, it's going to be perpendicular. It's going to be perpendicular to our axis of rotation. So we know we're going to use the washer-disk method. So for this one, we're going to go ahead and pull out a pi. Because again, we're all about y's, it's going to be from c to d. So this is not going to change on any of the problems. And so now we need a big R and a little r. So big R is going to be f of y minus x equals 0, right? This is x is equal to f of y. This is x equals 0, so it's going to be just f of y minus 0. So this whole distance right here. Our little r is going to be g of y minus 0. Again, the distance right here. So our big R is going to be f of y. And remember, we have to quantity square that. And then our little r is going to be g of y. And we have to quantity square that. And then dy. So hopefully with the washer-disk method, you guys are pretty good with that one now. Just be cautious about the fact there's no squaring in the shell method. There is squaring here. And remember that we have to do each little r separately. We don't put them together and then square them. All right, let's look at the next one. Now we want the line y equals c. So we want the axis of rotation to be y equals c. This one's really awesome for us because our curve is actually going to be flush with our actual axis of rotation. So again, these are parallel to each other. So since they're parallel to each other, we now know that this is going to be a shell method problem. So we're going to do c to d. And again, guys, this is always going to be c to d. So there's really no thinking here. Now this question gets a little bit more confusing about what the r is. So I want to make sure that you guys are really understanding this pretty well. So in this particular example, again, the distance from the axis to the rectangle is going to be your y. Okay, the distance from your rectangle to your rectangle. Sorry, the distance from your rectangle to your axis of rotation is going to be your y. I'm looking for what r is. Little r. I want this distance right here. I want from the rectangle to our axis of rotation. So we have to remember that if this whole thing here is y, this distance is actually c. So whole thing y, this is c. So whole thing is y. And this piece is c, and I want r. So c plus r is equal to y. R is going to be equal to, I should say r is going to be equal to y minus c. So our radius is going to be y minus c. Just take a look at that and think about that for a second. It will come to you. It should make very much sense. Because remember, r is going to be the distance from the axis of rotation to our rectangle. But this distance, we always make this x or y, again, from the axis of rotation to our rectangle. So that's the only tricky part of this particular example. And the rest of it's pretty easy. I mean, this doesn't change. And notice that it doesn't change, right? For shell method, our height will not ever change. It's just basically our radius. And that's the good thing about the shell method, how it's easy, is everything's the same thing except for the actual radius. So our final example is going to be y equals 3. Y equals 3. And so I like this question because, again, it's parallel, so it's another shell method problem. So volume is going to be equal to 2 pi. the integration from C to D. And again, ladies and gentlemen, I'm going to go ahead and write out the f of y minus g of y, because that's going to be the height, right? That's not going to change, over dy. The only challenge here is just figuring out what the radius is. So I chose this as our last example because this is easier to see. So again, our y is from our axis to our rectangle, and our little r, or our little radius, is going to be this distance right here from the axis of rotation to our rectangle. So this again is a good visual for this. Well, we're at y equals 3 here. So this whole thing is 3, and I want to subtract this distance y. So you guys can easily, say, okay, well, r plus y equals 3. Well, then r has to be equal to 3 minus y. So I can go ahead and say that my radius is going to be 3 minus y. And that's it. That's it. All right, so that's going to be all for this video. I'm going to do another video coming up soon that has a summary of everything in this unit. Area, cross sections, washer disc method, and shell method. So I hope this is helpful, and I'll see you guys in the next video.